Okay. The main content of this class is coming from this computer networking book. In this computer networking book, one big chapter is on networking security. So the main content for this class coming from the slides from this textbook. This is a very popular textbook. And the last part on the message authentication code, this is mainly coming from the slides from this. This is older networking textbook. I don't know if they have a newer version or not, but it's also a popular textbook on computer networking. Some students, you probably have already know all the concept in this class, in this lecture, but many students, then you may not fully understand all those security concepts. So I want to go over it, which is essential for you to understand most security problems and security setup in the current internet and software. In terms of encryption, people usually use this kind of diagram to illustrate the concept for encryption. It's node A communicate with node B or person B. So it's, I say, Alice and Bob. So A and B, they communicate. They send data to each other, but during this transmission channel, like through the internet or through the wireless communication, the channel could be eavesdropped by attacker. It's called a TRUDY or intruder. The attacker can eavesdrop the data to know what's the content in the communication. It could also try to hijack the connection. It could also try to modify the data transmitted between A and B. So encryption is basically computer security is to make sure that A and B, they can talk securely and without worry about all the attack in the middle. So that's the diagram. So what might the node A and node B be for the cyber world? The traditional way is like the client and server. So like a web client, a web server, email client, and email server. And some other applications like DNS servers, like a DNS server, there are a lot of DNS servers all around the internet. So all the DNS servers, they exchange data with each other. So you can think that A and B could be that. It could be routers, because routers need to exchange the routing table information with each other, basically find out what's the new routing path and share that information with each other to help the network routing. And two computers in peer-to-peer network, like when you download some files from another users, then your computer could be A, the other user computer could be B. A wireless laptop or like your smartphone and the wireless access point, like the Wi-Fi hotspot. Cell phone cell tower and cell phone Bluetooth earphone, and RFID tag and RFID reader, like in the store, in the sales, you could have RFID tag and RFID reader. And in smartphone, there's very popular way is the QR code. So you can think QR code and the QR code reader is one is A and another is B. So any kind of two entities, they communicate with each other, you can think in that diagram. What could a bad guy do? First is eavesdropping. Eavesdropping, it doesn't need a lot of techniques, and many communication medium allow a third party to eavesdrop on the channel. So quantum communication is trying to break down this attack, because eavesdropping, no one can defend against it in terms of the current electronic signals. But if you communicate through quantum computing way, then that can defend against eavesdropping, because anyone eavesdrop on the channel, the communication cannot go through, and the A and B, they will know that they have been eavesdropped. Actively insert message into the connections. So try to make A and B to have wrong communication. Impersonate is that impersonate as one to talk with the other. So A and B, they think that they are talking with the correct person, correct contact, but they're actually talking with the attacker. So attacker can impersonate A, or attacker can impersonate as a B. Hijack, it means take over the ongoing connection. For example, when you connect with your bank account, once you finish the login process, you suddenly find that you cannot connect to the bank account anymore. But actually, your connection may be hijacked by the attacker. The attacker will continue your bank account interaction with the bank server. On the other hand, the bank server does not realize that the communication has been changed to the attacker. So that is hijacking. Of course, hijacking needs a lot of attacking techniques. So it's probably the most difficult attack in terms of this four method. Denial of service is also one easy attack. So there are a lot of denial of service attack in the internet. Denial of service basically means prevent service from being used by others. Like try to overwhelm either A or overwhelm either B, so that A and B, their communication cannot go through normally. So that's called denial of service. This attack doesn't need attacker to have that much attacking techniques. So attacker does not need to compromise anyone. Attacker just need to use a bunch of zombie machines on internet to send a large flooding traffic to one of the node in terms of this A and B, the communication. So denial of service is a very widely used attack. Attacker use denial of service like mainly for example, many attackers use denial of service to gain a financial benefit, like they can blackmail a police department, blackmail a hospital, basically saying that if you don't pay the money to me, your service will be disrupted. So that is a denial of service attack. In terms of the language of the cryptography, mainly most of our slides is coming from that computer networking top-down approach book. So we will use the notations following that book. Many other books, they may use a slightly different notation to represent encryption and decryption. So A and B, when they send data, we say it's called plain text. And when the data is encrypted by Alice encryption key, we say this encryption key is a KA. And using a kind of encryption algorithm, then that data will become ciphertext. Basically, it is encrypted. And when it arrives at the node B, B can use the corresponding decryption key. So we note it as KB to decrypt it, to recover the plain text. So in terms of this relationship of KA and KB, the cryptography are classified into two categories. One is symmetric key cryptography. Symmetric key cryptography just means KA is equal to KB. So this encryption and decryption using the same key. And it's called symmetric cryptography. If KA and KB, they are different. So KA and KB is different, but they form a matching pair. When you use one to encrypt, then you need to use the other one to do the decryption. Then this kind of cryptography is called the public key cryptography. Or usually people say asymmetric key cryptography. So one is a symmetric key cryptography, another is asymmetric key cryptography. But usually we call this as public key cryptography because one key can be known by everyone. So that's called public key. Another key is only known by the owner. So that's called private key. So that's usually used for the asymmetric cryptography. So we will first briefly introduce the cryptography used before the computer age. Before computer, either mechanical computer or right now electronic computer, people manually do encryption and decryption, especially during war. So all those cryptography, we call them classical cryptography. The operation is basically classified in two categories. One is the transposition cipher, another is a substitution cipher. Basically, transposition cipher means that you just shuffle the position of those data. So it's just like a poker card. You shuffle a poker card to make it looks like random. Then the attacker, they will not be able to read the text. So you basically shuffle all the letters, all the symbols in your language, in your original plain text, in a certain way. Then the receiver use the same algorithm, same pattern to shuffle it back in order to return the plain text. So that's called transposition cipher. Another operation mode is called substitution. It's a substitution cipher. Just means for every symbol or every letter in the plain text, you substitute it with another letter in the language. So that's called substitution cipher. So we will briefly introduce some typical classical cryptography used in these two categories. Transposition cipher, the typical one is called the real fence cryptography. For example, you write the plain text in two rows in column order. Then you generate the ciphertext in row order. So, for example, for this plain text, hello world, you write it down in this column order and write it down into two rows. So HELLOWORLD. Then the ciphertext is, you generate ciphertext using this row order. So encryption is like write down in the column cipher, and decryption. So encryption write down, when you write down, then the ciphertext is the row order of the text. So the ciphertext, you can see that it's exactly the same letter as original plain text, but the order of those symbol, order of those letters has been shuffled. This shuffle pattern is basically using this so-called real fence. And you can think that this encryption key is 2. We can have an encryption key, an arbitrary value. For example, if the text is long enough, we can have an encryption key as like a 21 or 50. 21 means that you write into 21 rows using the same way, then you generate ciphertext. So this encryption key is basically how many rows you generate in the real fence. Of course, this can be seen that if attacker knows that you are using this real fence algorithm, then attacker can just enumerate all the number of rows before you write. Because your plain text is limited. For example, if your plain text has 1,000 character, then the number of rows you can generate is at most 1,000. If you generate 1,000 rows, then it's just a single column. So and there's no change of the order anymore. So So the key space is very limited. The key space is limited by the size of the plaintext. Attacker can just enumerate every possible key to write it down and to see which one can recover the meaningful plaintext. So this is not that much secure, but at least it can fool attacker that don't know that this writing algorithm. So this is a typical transposition cipher. Just shuffle the position, but does not change every symbols, every letter in the plaintext. Another issue is that it does not affect the frequency of individual symbols. So the original plaintext, you have 3L. Then the ciphertext, you also have 3L. So that doesn't change. For substitution cipher, one of the well-known substitution cipher is called a Caesar cipher because it has been used in the old Roman age. Caesar cipher is basically shift the alphabet. Suppose we use English as example. For other language, it's the same thing. For any language, you have alphabet, basic symbols. So for English language, this is alphabet 26 letters. Then you just shift the position by the fixed number, like a shift by 3. Then A will be shift to become letter D. B will be shift to become letter E. So that is a shifting order of 3. Then for this plaintext, you can see what's the ciphertext. Just I shift by 3 become L, so the first letter become L. So you just do that kind of shifting, you generate the ciphertext. And we can see that this is a very simple encryption, and decryption is also very simple. You just shift it back. However, we can see that this has clearly a big problem because of this key space. For English language, you only have 26 alphabet. So you can only have at most 25 shifting key. Because if you shift in 26, you basically shift back to the original letter. You doesn't make any change. So you only have a shifting key from 1 to 25. There are only 25 possible shifting key. If attacker know that you are using Caesar cipher, they only need to try at most 25 times, and then they can recover the original plaintext. So that's the problem for this Caesar cipher. It's very simple, but it's easily to crack as long as attacker know you are using Caesar cipher algorithm. Has a key with only, actually is a 25 possible value because 26, you're basically shifting back. You are not changing anything. Another problem is that for English text, for any language, it's the same thing. Any language, their text have statistical structure. For example, for English, the letter E appeared most. This is a statistical result of every alphabet in English literature. Like when people collect all the many English literature, they find which letter appeared most. This is the frequency. So letter E appeared most, clearly more frequent than the other letter. And the letter J and the letter Z, they appear least. So those two letters were rarely used. So what does this mean? The frequency analysis means? It means that for the ciphertext, we don't need to try 25 times. We just find which alphabet appeared most in the ciphertext. Then that alphabet has very high probability to corresponding to letter E in the language. So you just assume that the most appeared alphabet in the ciphertext corresponding to letter E. Then you just use that shifting key to try to decipher. And you probably can be successful in just one try. if you are not successful, then you guess that most appeared letter corresponding to the second frequent alphabet, like a second frequently appeared alphabet is letter T. You just try this according to the frequency, then you can be successful in just 2 or 3 tries. So you don't need to try all the 25 possible values. So that's so-called frequency analysis. In modern cryptography, frequency analysis is also one of the main techniques for people to crack encryption key for any encryption. Because no matter how you do encryption, you always have certain patterns. So you can reduce the frequency appearance, but you cannot completely make it disappear. You can only reduce the frequency statistic in the ciphertext, but you cannot fully remove it. So that's the 2 major problems for this CISA cipher. One is encryption key is space is too small. People can enumerate them. Secondly, it suffers against this frequency statistical analysis. And so for that reason, people think that the CISA cipher has a very good idea. It's very simple, but clearly it has these 2 weaknesses. If you want to develop a cryptography that based on CISA cipher, you need to at least solve those 2 weaknesses, at least reduce the problem from this 2 weaknesses. So one mathematician developed this called Wigner cipher in 1700 or 1600. I don't remember the time. But this cipher is basically try to resolve those 2 problems in a CISA cipher. The basic idea is that we still use a CISA cipher operation, but we use it in a different way. So for the plain text, we generate multiple shifting key. So every shifting key will use CISA cipher operation to do the shift. But the key right now is not a single digit anymore. For CISA cipher, we only have one key, is one shifting key. The shifting key is between 1 to 25. So for this original cipher, we have multiple shifting key. Suppose this original cipher have 3-digit shifting key, 2, 3, 4. Then you just use this 3-digit shifting key repeatedly, 2, 3, 4, 2, 3, 4, 2, 3, 4, to shift the original plaintext. So in this way, I will shift by 2 position, become K. A will shift by 3 position, become D. T will shift by 4 position, become X. So this will become the ciphertext. And you can see that it actually solved those 2 problems. First, the key space become much larger. Suppose you only have 3-digit shifting key, then what's the possible key value for this? Remember, every digit you have 1 to 25 possible values. You have 3 shifting digit key. So the possible key space is basically 25 power 3. So it's not a 25 multiplied with 3, it's a 25 power 3. So that's tens of thousands possible values for the key. Before we have any computer, these tens of thousands possible values is impossible for attacker to manually try every key value to crack the cipher. So that will solve this key space problem. Secondly, it can partially destroy this frequency analysis. It can partially destroy the frequency features in the ciphertext. You can see that like this letter T in the ciphertext, they become 2 different letters, X and V. So even though the original plaintext letter E appeared most, but in the cipher test, the letter E could corresponding to several different letters in the cipher test. So this will partially destroy the frequency feature. We say it can partially destroy because it's a key, we have to use it repeatedly, 234, 234, 234. So if the letter, like a letter A, these two letters is the same letter, if they differed by exactly multiple value of the number of shifting key, like if the letter A and letter A, they differed by 3 or by 6 or by 9 position, then when they do the shifting, they are shifting using the same digit in the shifting key. Then the cipher test, they become the same cipher letter. So in this way, their frequency will still be kept in the cipher test. So we say that this destroying this frequency, it's partially destroying the frequency. It cannot completely remove the frequency features in the cipher test. The reason is because this key is repeatedly used. Once you repeatedly use it, you will keep some pattern in the cipher test. So that's the regional cipher. And after people presented the regional cipher, the mathematician tried to think how can we break it. This is a method presented by this researcher in 1863 to break it. First, you try to guess the length of the regional cipher, how many digits used in this key. If the length is small, you can just try 1, 2, 3, just try out. But the more efficient way is find repeated string in the cipher test. As I said, this frequency is partially kept in the cipher test because you repeatedly use it. So if you check the cipher test, if you find some string is repeatedly appeared, then it's highly possible that they also corresponding to the same kind of string in the plain text, and their distance, this repeated cipher string, their distance should be multiple of the key value. Like if you find this repeated string in the cipher test, then their distance, like if their distance is 9, then you can guess that the shifting key should be either 9-digit or 3-digit. Then this cipher key could be repeated in a cipher test. So you use this way to guess what's the length of the shifting key. This is much more efficient way than just try it out. After you guess the shifting key, you just organize the cipher test in the rows with the same length of the key. So if you guess the shifting key is 9-digit, then you just organize cipher test in terms of 9 columns. Then every column is basically encrypted by the Caesar cipher by one shifting value. Just like here, you organize a cipher test in terms of 3 columns, then every column is shifted by the same Caesar cipher shifting key. Then you try to find what's the shifting key for that column. So using this way, you can decrypt the regional cipher. So this is a typical divide and conquer approach. In algorithm, divide and conquer is one main principle for many algorithm design. So this is like a divide and conquer. You divide this complicated problem into separate each column decipher, and each column decipher is a Caesar cipher. It's much simpler than the original regional cipher. So that's the divide and conquer approach. And we can see that the problem for regional cipher is because this key, you repeatedly use it. Once you repeat to use this key many times, you will keep some pattern in a cipher test. So that's the root cause for the vulnerability for Vigenère cipher. So a natural extension of the Vigenère cipher is that we make this key as long as a plaintext. Then the key will never repeat it to be used. Then there will be no pattern kept in the cipher test. So this is called one-time keypad. The key is as long as a plaintext. And people have proved that this is perfect secure. This cryptography is perfect secure because there is no statistical pattern kept. And there's no way for you to analyze it through frequency analysis. Of course, this one is not feasible for the computer communication because if you want to transmit some plaintext, you need to share that same size of the key to the other end. If you have way to share the same size of the key to the other end, why not just transmit the signal data through the first way? So it is only valid approach in the traditional spy world. Like a spy in the traditional spy war is like when you send out an agent, you give the agent a keypad. This keypad will have a lot of these numbers, a sequence of numbers, never repeat with itself. Then when you communicate with your spy, you just use this keypad. Once you use this key sequence in one page, you just rip this page off and destroy it. You will never reuse that sequence again. So that is like the same principle as a one-time keypad. So as long as your key string is randomly chosen, then this is perfect secure. No one can crack it. But of course, this means that code book can only be used once. You cannot reuse the code book. If you and your spy don't have enough code book, then the spy has to reuse the previous code book. Then you will have the potential problem to be cracked because you reuse that sequence of shifting key. And one researcher from MIT, he tried to present a feasible way for modern internet to use this one-time keypad. He is one of the developer of the public key cryptography. It's reversed. He was a professor in MIT, at least more than 10 years ago, but I don't know whether he still lived or not. Probably not. But anyway, at that time, I heard one of his seminar. He talked about how to use this one-time keypad by using satellite. Like he envisioned that there are some satellite. It's just like GPS satellite. The satellite just broadcast this sequence of random number. It broadcasts this sequence of random number without repeating itself. So this random number just keep sending out forever. Like the satellite broadcast like 100 number in every second. It send out. It just do this continuously. Then when you want to send data to your friend, you just capture the current sequence of number from the satellite. You use that to do this one-time keypad encryption. Then you send to your friend. And your friend, because this data will note what's the time what's the starting time for this data transmission. So your friend in real time, he will know that you send this data like 5 seconds ago or 10 seconds ago. Then as long as he can keep buffering this sequence for at least like a 1 minute buffer, like every computer, you just have 1 minute buffer of all the broadcast sequence. Then he will be able to go back 5 seconds to use that sequence to decipher it. And then you can have this data communicate. How to make this against this attack? It just assume that this sequence, the broadcast is going on forever. So if someone want to decrypt the data transmitted like 1 year ago, it's not possible for him to do that because he don't have the storage to save all the sequence up to 1 year ago, because that's too many numbers. So that's the idea he presented. Basically, using this storage capacity as the buffer to prevent this reuse attack or crack after some time. That's a basic idea, but I don't know if he has published any paper on that or not. Anyway, that is this classical cryptography. Basically, this transposition cipher and substitution cipher. In modern cryptography just talk about any cryptography designed after computer become reality. So when we have computer, how do we design cryptography algorithm? First is the symmetric key cryptography, because this is easier to design considering the current computer architecture. The plain text, we use M to represent plain text. And the encryption key, decryption key, because it's a symmetric key cryptography. So encryption, decryption, it's the same key. And in James Kruse, the networking book, it uses a KAB to represent the key used between node A and node B. So this is a key shared between node A and node B. And the cipher test is the KAB encrypting of this message M. So this is notation. Some other textbooks, they use different notation to represent the encryption. And for the receiver uses B to decrypt the algorithm, this cipher test, and recover original plain text. So this is the notation. So the one major problem for this symmetric key cryptography is that before you send the data using this encryption channel, you need to share this common key between node A and node B. So if node A and node B, they are two computers on the internet, how do you share this secret key between them before you have a secure channel set up between these two nodes? So that's one major issue that need to be solved in order to make symmetric key cryptography usable. The first modern symmetric key cryptography is developed by the US government. It's called DES, Data Encryption Standard. It was developed in late 1960s, early 1970s. But at that time, it's a country's secret. So it never shared this algorithm with others. So it's a country's secret. It only became a public known algorithm and become a public standard in 1993. So in 1993, it became a public standard. And it's called a block cipher. Basically, it divides the plaintext into many blocks. Each block is 64-bit. Then you use this encryption key is a 56-bit encryption key to encrypt every block. So that's called block cipher. And it was developed in late 1960s. So when it became public standard, people try to find whether there is any backdoor set up by those developers. But until now, people still have not found any backdoor set up in this algorithm. And this algorithm became public because in late 1980s, early 1990s, computer speed is so fast that 56-bit encryption key become too small. because 56-bit encryption key just means this key space is 2 to power 56. So in 1960s, people think that this 2 to power 56 is such a large key space that it is immune to any enumeration attack. But just after 30 years of the computer development, in early 1990s, you can use a high-speed computer, a good server. You can enumerate all the possible key values in terms of hours or a few days. So it's not secure anymore. As long as attacker have a good computer, they can enumerate all the possible key to find the encryption key within several days. So that is a time when people realize that we need to develop a new algorithm to replace it, because this encryption key is too small. But because of this 20 to 30 years usage of DES, there are many software program the DES encryption in it. Furthermore, there are many hardware chips. They build in the DES encryption into the hardware chip. Because building hardware chip will make the encryption decryption much efficient. So many devices, they already build in DES algorithm into the chip. If you want to replace them, then that means you need to replace a lot of older device, and it costs too much. So people think that how can we extend the lifetime for those DES chip? However, we want to make it more secure than the older DES algorithm. The basic approach is that they develop a so-called triple DES algorithm. The triple DES algorithm is very simple. It's just we run this DES encryption 3 times, and we use encryption key is also 3 times of 56-bit. Then every time we go through the DES chip, we use just 1/3 of the encryption key. So encryption key is large, is 168-bit. That's overall encryption key. So first time we run through DES encryption chip, we use the first 1/3, 56-bit encryption key to go through the encryption. Then we use the second third part of the encryption key to go through the DES chip encryption again, then go through it again. So in this way, we don't need to change the DES encryption chip. We just need to change some control chip. Like if you build a board, you don't need to remove the DES chip. You just add a simple controller logic on it to make this encryption to go through the DES chip 3 times. In this way, it will solve this key space problem. It will make the key space become 3 times longer. Remember, this key space 3 times longer does not mean this key space is 3 times longer, because if you increase the key by 1 bit, you basically double the key space. So that's how you can enlarge this key space. So triple DES is still widely used right now because no one has found any vulnerability in DES itself. It's just the key space is too small. So triple DES is still widely used. And this is the basic diagram for DES encryption. And DES encryption is basically a combination of transposition and substitution in the classical cryptography. So even though classical cryptography is become outdated, but the basic principle is still valid, the transposition and the substitution. So this is a plaintext 64. What? I'll talk to you on P2. Okay. Okay, you have a meeting? Yeah.
Sorry, excuse me.
Yeah.
I'm over here done, my sweetheart. Can you go and talk to me in P2? Because they have not told me this class was here and I already had things.
Oh, okay.
Okay?
Yeah. Yeah, last year. Okay, we can change to a smaller room. Yeah.
Yes, I can log in what it is.
Okay. Okay. Yeah.
And what will happen again, because I'm overbooking, not knowing there's somebody here.
Okay.
Thank you.
Thank you. Okay, this is the data, the plain text data. It first goes through this transposition. So basically, you have it's called permutation. It's like you shift all the 64 bits according to a prefixed order. So this shifting is fixed. So there's no secret here. If this DES algorithm become public, the attacker also know this shifting rule here. So this is not secret. Then after you have the initial transposition, you divide this 64-bit into two words. So left is 32-bit, right is also 32-bit. And then you take this right side 32-bit out, you make it as input to this. It's called a substitution box. It's like a Caesar cipher that substitution. It's a substitution box. This substitution box will have three input. The left side 32-bit, right side 32-bit, and this 48-bit K1. This K1, K2 until K16, they're all 48-bit. They were expanded from the encryption key, 56-bit encryption key. So you can see that K1 to K16, they are actually correlated with each other. They are not independent. Because originally you only have 56-bit encryption key. Now you need to use it to generate 16 keys. Each key is 48-bit. So you can see. And this expansion is also predetermined. So it's not a secret. Once the algorithm is known by everyone, then this expansion is also known by everyone. So there's no secret here. So this substitution box, you can think that this is like a lookup table. This three input, you can think this is like the index to the lookup table. Then the entry in the lookup table will become the output. The output will become R2. The left 2 is 32-bit. You directly move this right-hand 32-bit out to become here. So you only change this 32-bit. The left side 32-bit, you directly move this 32-bit down. Then you run this operation repeatedly for 16 times. You run this operation repeatedly for 16 times. Then after that, you run another transposition. Again, it's a prefixed, so there's no secret here. Then after that, that is a ciphertext generated. So this is ciphertext generated. So this is a basic flow for the DS algorithm. For the substitution box, as I said, you can treat this as a table lookup. You can find some example of the substitution box. Like a DES substitution box. Um, Okay, this is a permutation. Permutation is basically you pre-shuffle according to a fixed position. So that is permutation. It's a it is put it here, and the substitution box is S1 to S. Well, it only lists S1 to S8, and this S1 means the first round of a substitution box. So every round, the substitution box is different. This table lookup box is different, and you can see that this is simplified substitution box. Substitution box right now in the algorithm, it has 3 input. So you can think that 3 input is like a 3 index. In the Wikipedia, it only show the partial box. So you can think that this x-axis, y-axis is the 2 input. Then the 2 input will generate an index to the table. Then that table's entry value will be the output of the substitution box. So that's so-called substitution box here. And it seems the developer of the DES, they randomly defined the value in this substitution box, because no one had found out if there's a backdoor in a substitution box. It just seems randomly number put in this substitution box. If you want to know more, you can go to Wikipedia and just search DS this one. Oh, okay. So this is a rough diagram. This substitution box is actually not using this 3 input as the table lookup. It actually, the table lookup, the substitution box is here. It only uses 2 input as the table lookup. So this table is still 2-dimensional table. It's not a 3-dimensional table. So the 3 input is further refined in here. This is a substitution box, has the 2 input. One input is this key. One input is this right side 32-bit. Then the output will XOR. This plus in computer logic represent XOR operation. So the output will XOR with the left side, then generate the output. So you can, if you treat the entire thing here as the S box, then it will have 3 input. But actually, the substitution box is here, so it only have two input. That's why this Wikipedia, it showed this substitution box is 2 input to generate this substitution box. 6-bit input with a 4-bit output. Oh, I copied these slides from Dr. Brandon Wang's class. He teaches this class in UCF. I borrowed a few slides from him. And so this is F function, is this substitution box. And this is the F function. The further in F function is that this is the right side 32-bit. This is the key 48-bit. It goes through this operation. So the icebox is the B. the B here is basically 6-bit will become 4-bit, and there are 8 icebox, and so icebox are the only nonlinear element in DES design. You need to have a nonlinear element. If every transition is linear, then it can be easily reverse back. So you need to have nonlinear to make it impossible to reverse back. So this B here is that okay, I will not introduce detail of the icebox things. So when the DES become outdated and people begin to develop the second generation of the symmetric key cryptography, and people have developed many such kind of cryptography, then the US government picked one of them as a standard to be used by the government organization. This algorithm is called AES, Advanced Encryption Algorithm. Just to remind you that this is just one of the many, this second generation symmetric key cryptography. It doesn't mean it's the best one among them, but it just means this is one picked by the government. And it's become NIST standard in 2001 to replace DES. The data block become bigger because our data transfer is much bigger than the 1960s and 1970s. So the data block become bigger. The key size also become bigger. It can support 3 different lengths of the key. So if the key length is longer, that means your encryption and decryption will take more computing resource, but you will be more secure because the key space is larger. Larger, of course, the key space will become bigger. But AES, the design, the principle is actually the same as DES. So DES is a very successful design. So all the second generation public key cryptography, they use the same design principle. It's just a slightly different, but basic design is the same. They all have the similar way of here. They all have the similar way of the substitution box. Then using the substitution box multiple round to generate a ciphertext. They all have this permutation in the beginning, permutation at the end. So they all have all those operations. All this modern cryptography, they all have the same kind of operation. Because that's why they all belong into this block cipher. Treat every data chunk as one block to do the encryption. So multiple paths of the same module, and so it's called block cipher. And for block cipher, if you use it directly to encrypt every block of data independently, then there is one major weakness. The major weakness is the appearance of the same block. Like in your plaintext, like in the web transmission, in every web request, you always have HTTP 1.1 in every request. So this text string appeared a lot in web traffic. If they happen to be in 2 different blocks, then the block cipher means their ciphertext is exactly the same, because you encrypt every block independently. So if these 2 blocks, they happen to be the same plaintext, then the ciphertext will also be the same. And the problem is very clear, just like in the region cipher. If attacker find there are repeated same string in the ciphertext, they will suspect that they corresponding to the same string in the plaintext. And if this is web traffic, then they highly possible to corresponding to this this HTTP/1.1. So they will have a matching plaintext and ciphertext. If attacker have a matching plaintext ciphertext, it can help them a lot in crack this cipher key. In addition, without a decryption, this will reveal a lot of content. I think Wikipedia explained that. If in Wikipedia, if you search blockchain, maybe not Wikipedia, but okay, I couldn't find it immediately. Let's come back to here. Okay, so if we encrypt every block independently, we will have this weakness. To resolve this weakness, a simple operation is called block chaining operation for the cipher. Basically, you try to make sure that so this is one operation of the block chaining. Like for this plaintext, you do not do the encryption on it directly. You first XOR with the previous block's ciphertext. The XOR result will go through this DES encryption. You generate this ICE block ciphertext. So you can see that now this each block's ciphertext is not only determined by this block's plaintext, but also determined by the previous block ciphertext. So you have this dependency between series of block. In this way, if these two block, they have exactly the same plaintext, the ciphertext will become different because of this correlation of one block with another block. So this is a cipher. It's called cipher block chaining. And there are many ways of cipher block chaining, like in the Wikipedia. This block cipher mode operation. Okay. Here has a reason why this cipher block chaining is needed. Like for this original image, if we use DS to encrypt without using this cipher block chaining, we just encrypt every section of the image independently using DS encryption, then this will be the encrypted image. So the encrypted image, even though every block become unreadable, but for the same content of the block, the ciphertext will become the same ciphertext. If you draw the image out, it becomes this one. And you can still see the rough contour, rough image for the original plaintext because you still kept a lot of pattern in the image. Without using block chaining, this is a ciphertext. By using this block chaining mode, this will become the ciphertext. It will become totally unreadable. So that's why this cipher block chaining is really needed. One operation is like a cipher block chaining is what I show in my slides. The previous ciphertext XOR with this current block plaintext. You go through the DES encryption, you generate ciphertext. So this is one block chaining method. It's called CBC. But there are many other operations as well. Like this is this PCBC method. It's basically previous block's ciphertext XOR with the previous block's plaintext, then XOR with current block plaintext. You go through this encryption. So that's another way to make this correlation. So there are many different ways to make this correlation. Each blockchaining method have its own advantage and disadvantage. So this is a cipher blockchain, and okay, so that's the symmetric key cryptography. So symmetric key cryptography, especially DES, every symmetric key cryptography is based on DES. So its operation is basically shifting and table lookup, and shifting again, table lookup again. So the design is using this computer architecture in mind, because current computer architecture is very good to do this bit shifting and also table lookup. All memory lookup is a table lookup, right? So it's very efficient for the current computer to run this symmetric key cryptography. It's very efficient. You can build a hardware chip very easily. And this multiple round of operation of the DES, that design is basically considering hardware in mind. Because in hardware, you can build this hardware chip, you go through it 16 rounds, like DES, you go through that basic operation 16 rounds. So you can build that hardware circuit and you run it 16 times, you can generate DES encryption. So it's all very efficient. But there's one major problem for symmetric key cryptography is that it requires the sender and receiver, they share the same secret key before you have a secure channel. So that's the one major issue for symmetric key. How to agree on the key in the first place, particularly if A and B, they never met. In the cyber world, it's very common that A and B, they never meet with each other. So they don't have a pre-shared secret between them. Now, how do you establish this secure channel before you have a secure channel to distribute this key? So that's one problem. That's why people presented this so-called asymmetric or public key cryptography. They try to make sure that it has a pair of keys, then one key can be shared publicly without worry about attacker also know that key. It uses a very, very different approach for the encryption and decryption. Actually, it is based on number theory. In a symmetric key cryptography, it's based on transposition substitution, based on shifting and table lookup. Public key cryptography, on the other hand, it is based on number theory. Number theory basically means that you do all the integer number, the operation of integer number, multiplication, division, plus, minus. So that's the number theory. So in public key cryptography, the plain text you can encrypt using Bob's public key. So for each user, you can generate a pair of key. One key is called private key. You keep it to yourself. You never share this secret key out. So it's called a private key. Notation is a KB minus. On that hand, the other part of the key is called public key, KB plus. This KB plus, you can broadcast it out to everyone. So you don't worry about attacker also know this KB plus. Then when Alice wants to send data, Alice uses KB plus to do the encryption. Because KB plus is broadcast out, so Alice can get it easily. And of course, attacker can also get KB plus. But attacker can only see this ciphertext. Only the owner of the KB miners can do the decryption and recover the plaintext. So that's the basic principle for this public key cryptography, is that the ciphertext is out there. Everyone can see it. Attacker also knows the encryption key, but attacker cannot decrypt it. Only the owner of the private key can decrypt it and recover the plaintext. Let's take a 10 minutes break. Right now it is 11:43, so let's meet back at 11:53, and we will finish the second half of this class. Let's take a 10 minutes break. Okay, let's resume the second half of this class. Any questions so far for the?
How do they do the decryption?
Do which one? The symmetric encryption or the public key encryption?
No. I guess it's the same as encrypted, but the other way around.
So the basic public key cryptography, they all following the same similar procedure. This is DES, the procedure for DES, but for AES, for other second generation symmetric key cryptography, their operation is almost the same. It's a shifting, like this right side to left side, right side to left side, shifting, and this substitution box. Of course, the content for the S box is different. Like DES, it seems S1 to S8. Each table lookup, the value in the table seems randomly chosen, but it's always fixed for DES. For AES, for other algorithm, the substitution box, the value is different, but it also seems to be randomly chosen. There's no pattern people can say, but all the operation, it's very similar to this. And as I said, AES is not the only one. There are many other symmetric key cryptography is symmetric key algorithm. Like the AES, the common algorithm. So these are the common algorithm used, like AES and blowfish, serpent, twofish. These are all in a similar role as AES, but they were not chosen by the government as a standard, but they have the similar encryption power as AES. The operation is also very similar to AES. And if you're interested, you can check them. So this is developed by this well-known cryptographer. Twofish. You can see it was one of 5 finalists for the advanced encryption standard contest. It was not selected for standardization. But they could be used by many other software as well. It's just not the US government standard. Okay. For public key cryptography, and And it has this requirement is that when you use this two key, you can recover the original plain text. Secondly, given that you know this public key, it should be impossible for attacker to compute and find out what's the corresponding private key. So that's the basic requirement. That attacker can know the public key, but attacker cannot find out what's the corresponding private key for the decryption. And the main algorithm is the RSA is developed by these three researchers, Rivers, Shamir, and Anderson. And Rivers is the one I said that he was the MIT's professor, and he tried to use this satellite to realize this one-time keypad for the modern computing world. But seems it's not widely deployed yet. It's not used. So these three researchers developed this public key cryptography. The basic principle for this RSA algorithm is that, remember, it is based on number theory. So it's very different from this transposition, substitution, table lookup in the DES algorithm. It's based on number theory. So you first choose two prime number, P and Q. It's a prime number. It's two very large prime number. You compute the product of these two prime number. You also compute the product of each prime number minus one. So you compute this as Z. Then you find out a E value that has no common factor with Z. So it's called relative prime. In number theory, there is a mature algorithm that you can find out a relative prime number. Given a prime number, you can find another relative prime number to that given number. There are existing algorithm to do that. Then you choose a D such that ED minus 1 is divisible by Z. So basically means that you find a value D such that ED modulo Z is equal to 1. Again, there are existing algorithms that you can find this number D out. After that, the public key is basically value N and E. The private key is value N and D. So you can think that the private key is basically D because N is already given in the public key. So attacker also knows N. Attacker knows N and E, but attacker has no way to find out what's the corresponding value D here. So that's the principle. Basically, it's based on the reason that given two large prime number, you can calculate their product N very easily. But given the number N, there's no easy way for you to find out what are the two prime number that product together equal to the given value N. So that's the basic principle. There is no existing algorithm to find the reverse order. Given P and Q, you can find N very easily. But given N, there's no easy way to find what's the value of P and Q to generate this N. The only way for you to do it is enumeration. Enumerate all the prime number you can find to run the product to check with whether it is equal to N or not. And if this value N is very, very large, then the enumeration will take forever for you to compute. To do the encryption, suppose this plain text is M, and you do the product. How do you do the encryption? Suppose this encryption, the plain text is this ASCII character. It's like an English language ASCII character. Then you treat every character as one value. every character is 1 byte, is within that 1 byte, right? So it is value between 0 to 255. So you basically encrypt every character to go through this algorithm, to go through this operation. So every character, you find its value between 0 to 255. You do this power computation, M modular, M power E, then modular N. Remember this public key is N and E. So you know this N and E. You do this power computation and modular computation. Then that is the cipher test. Then for the receiver end do the power D because the private key is the value D. So receiver end, you do this power D, then you modular N, then you can recover the original plaintext M. So you do this computation for every byte in your ASCII string, then you can do the encryption and decryption. The magic thing is that this is encryption result C. And when you do the power D, and you can recover the original plaintext M. And this encryption and decryption, they actually follow the same operation. It's just the power factor is different. One is E, another is D. Why this works? So let's give a very simple example. Suppose when you generate this public key, private key, the Bob choose this 2 prime number 5 and 7. Then he can calculate that N is equal to 35. The Z is 24. You find a number E such that E and Z, they are relative prime, like 5 and 24, they are relative prime. They don't have any common factor. And you find a D such that ED minus 1 is divisible by 24. So this is all the value you find. Then you do the encryption. For letter L, you can either use its ASCII value, but ASCII value is between 0 to 255, which is too big. But you can represent every alphabet by its position in the alphabet table, right? So letter A is value 1, letter B is value 2. So you can use that to represent each letter, which makes this number smaller. So letter L, the position is 12. So you can treat that its plaintext is 12, number 12. Then you do this 12 power E, 12 power 5. This is number, and you modular N, it becomes 17. So cipher test is 17. So what's the cipher test? The 17th position in the alphabet. So that letter is the cipher test. Then in the receiver end, the receiver find that that letter is the 17th position. So cipher value is the 17. You do the power D operation. D is 29. So this is a power computation result. Then you do modular N. You can recover the original value of 12. Then you can recover original plaintext L. And from this computation, you can see that this P and this Q, it's so small. No one can use that. And even for such a small prime number, this power computation can be easily to become very, very, very big integer numbers. Of course, in real computation, we don't need to compute such a big number because this is there is a modular N operation. So whenever you remember, power computation is like you multiply multiple times to that power value, right? When you multiply once, you do modular operation to make it smaller. Then you do multiply again, then you do multiple operation. Because the modular operation will make this result to be always smaller than this modular value here. So you do multiplication than modular, multiplication than modular. And there are some other algorithms can make this power and modular operation a more efficient way than just multiply modulation. But still, it's a lot of computation because current computer architecture is very easy to do shifting and table lookup. But power computation means multiplication. Multiplication needs a lot of computer clock cycle to do it. Like when you do assembly language, you know that plus minus is very easy. Plus minus computer can do very easily. But multiplication means each multiplication computing need many cycles of plus minus to compute. So this computation is very expensive to do. It's not like efficient like the symmetric key cryptography. In real world, like the prime number, you should choose very large prime number, like each one is 1,000 bit size of that prime number. Okay, why this computation will recover the original plaintext? Because in number theory, there is a number theory, it's called this. If P and Q and prime and N equal to PQ, then this equation exists. This equation, like when you modulo N is P and Q. When you have two arbitrary value X and Y, do the power and the modulo N, it is equal to, you first do the power value to modular P and 1, P minus 1, Q minus 1. Then you do this power and modulation operation. So if we use on the RSA algorithm, it just means RSA algorithm. So this is RSA algorithm. When you do this, it's this modular computation, you can do it anytime. It doesn't affect the multiplication result. So this one is equal to M module power ED. Then based on this theory, we can do ED modular P minus 1, Q minus 1. It will be the same result. So this is using this previous number theory. This number theory has been discovered a long time ago. It's discovered 100 years ago. It's not like discovered by this RSA. These three researchers just find out that this number theory has its usefulness in this encryption. The number theory has been exist a long time. And so this is equal to this one. And because we chose ED is when ED, remember in our algorithm, ED is chosen such that ED modular Z, because P minus 1, Q minus 1 is a Z. So ED modular Z is equal to 1. So this power component become 1, become M modulo N. M is much smaller than N. So it is equal to M. So in this way, we can recover the original message M. So that's why this RSA works. When you do encryption, when you do decryption, you can recover the original message M. So basically, these three researchers try to discover what kind of number theory we can use to utilize to generate this asymmetric encryption. They find out that this theory can be used to do that. And so that's why they develop this RSA algorithm. And there's another important feature for RSA algorithm is that you can use these two keys in reverse order. You can do encryption using this private key. Then you do decryption using this public key. Because you can see this operation. This D is a private key, right? Is used by the decryption. This E is used by the encryption. But if we change the position of the E and D, if we shift the value D and E, shift their position, this formula is exactly the same. It's just like a product. Your product A product with B is equal to B product with A. So they are interchangeable. For this formula, you can exchange a position of E and D with each other without changing the output of M. So you can use this M power D first. So you use this private key to do the encryption first. Then you use this public key value E to do the decryption. Then you can recover the original message. So basically means that you can use private key to do the encryption. Then you use public key to do the decryption. You can recover the original message M as well. So this is a very important feature that is very helpful in public key in the application of this asymmetric cryptography. And one usage of this reversed order of encryption is used in this digital signature application. So digital signature is analogy to the handwritten signature in the physical world. Handwritten signature is very useful in the physical world for document signing, for legal judgment, for the contract for legal judge, because it can prove that someone have approved and reviewed the document. In the digital world, how do we implement the same function? So that is using this public key cryptography to implement that. Basically, the sender, when the Bob send out a document, Bob will digitally sign the document, establishing that he is the document owner and creator. Then this document is verifiable, non-forgeable, means that the receiver, the Alice, can prove to others that Bob and no one else have signed the document. So that is in analogy to the physical signature in the real world. How to do that is that when Bob generate a message M, Bob use his private key, KB minus, to do the encryption. So this is encrypted message. But remember, this encrypted message is not a secret because attacker also know KB plus. Remember, KB plus, the public key, is shared to everyone. So not only the receiver have it, attacker also have it. So attacker can decrypt and read the message. So this encryption is not for secrecy purpose. This is only for digital signature purpose. Then when Alice receives the digital signature, Alice verifies M by applying Bob's public key to the digital signature to check whether this decrypted result will match with the message he received. If the decryption result match with the plaintext message he received, then whoever sent the message M must have used Bob's private key. If we assume Bob's private key is securely held by Bob, then we prove that this document is really signed by Bob and is not signed by anyone else. And attacker have not modified the message, because if attacker modify the ciphertext, when Alice do the decryption, you can only recover this garbled message. You will not recover the original message. So if you recover the original readable plaintext, then you know that it is signed by the sender. No one else has modified the message. So Alice can verify that Bob has signed the message, no one else signed the message, and the message has not been modified by anyone else. Non-reputation just means that it can be used as a legal contract. Alice can take the message M and signature to the court and prove that Bob has signed the message, just like the the physical signature in the physical world. And there is one problem, one issue in this application of the digital signature is that if the message is big, these KB miners will take a lot of time to compute. Remember this public key cryptography, this is built based on the number theory. It needed this power computation. So it's very, very slow compared to symmetric key cryptography. So doing this digital signature will take too much computation resource for both sender and receiver. So people find a way try to resolve that issue by using this so-called message digest to do that. So instead of encrypt the original entire message by these KB miners, we only encrypt the hash value of the original message by KB miners. So we only encrypt using this private key to encrypt the hash value. The hash value is much smaller, like it is only like 16 bytes or 20 bytes. It's only like dozens of bytes. So if you use a private key to do the encryption, it doesn't take that much time. No matter how large the original message is, no matter whether the original message is megabytes or gigabyte, the hash value is always 16 bytes or 20 bytes. And this hash function is called a cryptography hash. Because this hash function have this property, of course, this is still many-to-one mapping. It just means that it's possible that two messages, they can generate the same hash value. Because the hash value is only 16 bytes or 20 bytes, it's very possible that the two original messages generate the same hash value. However, the cryptography hash requires that given a message digest, it's computationally infeasible to find a message that can generate that hash value. The principle is a little bit similar to this RSA algorithm. So here it just means that going this way is very easy. Given you a message, you can easily to compute the hash value. But given a hash value, it's impossible to find a message M that can generate that hash value. So one direction is very easy. Reverse direction is almost impossible. So that's the principle for how do you choose this cryptography hash. Some hash function does not satisfy this. Like last class when I introduced networking like TCP packet header, IP packet header, the two packet header, TCP header, IP header, they all have checksum. Checksum, you can treat that as a hash function because checksum only 16 bits, but packet is much larger than 16 bits, right? No matter how large the packet, the checksum is always 16 bits. So you can treat the checksum algorithm is a type of hash function. But checksum is not a good candidate for this cryptography hash because checksum computation is basically you treat every 16 bits in the packet as one data. You add all of them together. You just ignore this carry-on bit. Then the final result is a checksum. And it's clearly, you can see that if you change 2 bits in 16 bits data, you flip both bits, the checksum will not change. So it means that given a checksum, you can easily modify the packet, flip 2 bits or flip 4 bits, they generate the same checksum. Cryptography hash, on the other hand, does not allow you to do that. If you modify a message, no matter how you modify the message, the checksum will be different. How can you make the checksum not change? You probably need to enumerate every modification of the message in order to make them happen to generate same checksum. So that's computational impossible. So cryptography hash need to be carefully designed. It's not like as simple as the checksum hash function. The cryptography hash is basically designed. Well, I will explain this in a moment. Right now, there are two popular cryptography hash used in the cryptography field. One is called MD5, another is SHA-1. MD5 actually was designed by Rivest, the first author in the RSA algorithm. So he is also the designer for the MD5 hash algorithm. It's a standard. It has been widely used. MD5 means this is the version 5 of the message digest algorithm. The previous version, they have this and that problem. This is the number 5 version. It becomes stable and people widely use it. It computes a 128-bit hash value. So it's 16 bytes. So the hash value is always 16 bytes, no matter how large the original message. And it find out that given you a hash value, given you this 16 bytes hash value, and given you the original message that generate this hash value, you don't have an easy way to modify the original message without changing the hash value. So that's the principle. Difficult to construct a message M whose hash value is equal to the X. So reverse, it's computational infeasible. You have to enumerate all the possible modification on the original message in order to generate the same hash value as original message. So that means that if attacker modifies the original message, no matter how attacker modifies the original message, the hash value will always change. So you cannot change the message without not changing the hash value. But MD5 in 2000, I don't remember, 2004, 2005, there's a major breakthrough in cryptography research. One researcher found out a major vulnerability in MD5, such that it makes this try out. You can try out much smaller times in order to modify the message without changing this hash value. So people have found out a much more efficient way to do that cracking. So MD5 become not secure anymore. Then quickly people design some other hash algorithm. This SHA-1 is the standard, is the one picked by government, US government as a standard. So again, just like DES and AES, in the AES, there are many other algorithms. It's just AES picked by the government. SHA-1 is picked by the US government as a standard, but there are many other second generation hash algorithm designed as well. The design principle is like here. This is MD5 design principle. Remember, this hash algorithm is not encryption, so it doesn't have a secret encryption key here. So you break the original plaintext into many blocks. Again, the design principle is similar to DES, to AES, to the DES as well. Everything is you can come back to the original DES algorithm design. So you break the original plaintext into many blocks. Each block is a B bit, and another input is initial vector. This IV is initial vector. Again, this is not an encryption key, so everyone use the same initial vector value. So this is not a secret. And you go through this F function. This F function is very similar to the substitution box in DES. You go through this, you generate the output, Then you use the second block of the plaintext as the input. You go through the substitution box again. Then you just repeatedly go through every block of the data until in the end, the output is that 16 bytes hash value. So this N for MD5 is the 16 bytes. And initial vector is the predetermined, is always known for everyone. So that's how the MD5 works. That's also how the SHA-1 works, SHA-1. Every hash algorithm, they are using a similar principle. Any question for this cryptography hash? The design principle, why the checksum hash algorithm does not work for this cryptography hash. So SHA-1 is 160 bits, but there are some variation of the SHA algorithm, like a SHA-256, SHA-518. Basically, SHA-256 means this hash value is 256 bit. The original standard is 160 bits for the hash value. So when we have this cryptography hash, how do we make this digital signature applicable? Because original digital signature, this private key encryption is too much computation. So in the digital signature in the real world, the large message will first go through this MD5 hash algorithm first to generate this hash value. Then the sender use receivers, the sender's private key to do the encryption on this 16 bytes or 20 bytes hash value. The encrypted result is the digital signature. So this is called digital signature. The hash value goes through this encryption. The encryption is using the private key to do the encryption. Then in the receiver end, the Alice receiver end, receiver will receive both the message and the digital signature together. So the message is not encrypted. You can treat that is like a public contract. So you don't worry about attacker know the contract information. You only worry about digital signature. So the original message is a plain text. When the receiver receive it, receiver use the same hash algorithm to generate the hash value. Receiver use the sender's public key to do the decryption because public key is known by the receiver. Then receiver compare these two hash value. If they equal to each other, then it means that the digital signature has been verified. The message M is really generated by Bob. And it has not been modified by anyone. Because if attacker modify the message M, the two hash value will be different. So that's how the real world, in the real world, how the digital signature works. Digital signature is always using this public key cryptography encryption on the hash value. It never encrypt the original message directly. It always do the encryption decryption on the hash value. So this page of slides is very important. Any difficulty in understanding this page of the operation of the digital signature? This plus, you can think that it's concatenate. The sender send a message plus the digital signature out. If you want to do XOR, it's also you can do XOR operation as well. It does not matter that much, because receiver you can do XOR to get both parts out. But normally it's just concatenate. Of course, this digital signature only serve this also authentication purpose. It doesn't serve the confidentiality issue. In computer security, confidentiality is the #1 requirement, but authentication is another major requirement for security. So this one achieves the authentication or integrity in the cybersecurity. Confidentiality requires some others to achieve it. So that's the digital signature. Another use of the public key cryptography is to help the key dissemination for symmetric key cryptography. In a real communication, we need to provide confidentiality. We need to encrypt the entire message. For encryption of the entire message, we have to rely on symmetric key cryptography. But how can we distribute the symmetric key between two entities? That one, we need to rely on this public key cryptography to do that. So in the internet, there is one big problem is how do we disseminate a key between sender and receiver? How do two entities establish shared secret? For this one, we can use a solution. It's called a trusted intermediary to do that. It's just like A and B, when they talk to each other, it's difficult for them to establish this shared key. But they can have a trusted key distribution center as the intermediary to help them to do that. But even for public key cryptography, it can solve this key dissemination. But in the internet, how do you distribute the public key in a reliable way? Because we assume that the public key can be broadcast to everyone. So there is no problem for that. But in the internet, even the broadcast have its own problem. Like when you want to send data to Bob, you need to know Bob's public key. One way that is Bob publish his public key on his website. But when you connect to Bob's website, how do you know you connect to the real Bob's website? You are not connecting to an attacker's fake website. Another way that you receive Bob's public key through email, like Bob send his public key through email to everyone. But how do you know the email you receive is really generated by Bob? It's not generated by attacker saying that, well, this is Bob's public key, but actually it's attacker's public key. So even for public key dissemination, it still has some problem. How does the receiver know that it is Bob's public key, not attacker's public key? Either website, email, or mailed disk, storage, all these ways they have some problem. So again, we still need a trusted intermediary to do this key dissemination. And this is the way realized in the internet. This KDC is not realized in the internet because it's too difficult. And this CA-based key dissemination is feasible and has been widely used in the internet. Let's explain what's the principle behind the KDC way. KDC way is that suppose Alice and Bob, they want to distribute their secret key securely to each other. They first register with a KDC center. This KDC center could be like a driver license office. You physically go to driver license office, you establish a shared secret key between yourself and KDC. This key means that this is a symmetric key shared between Bob and KDC. This is the secret key, symmetric secret key shared between Alice and KDC. So KDC have all the secret key for each user. So KDC have all the key for every user. Then when Alice wants to talk with Bob, Alice will first talk with the KDC by using Alice's secret key. So Alice encrypt this A and B encrypted sent to KDC. Remember this KDC is a shared key between Alice and KDC. So KDC is able to decrypt it. So KDC knows that Alice wants to talk with Bob. So this A and B means that this is identity for Alice and identity for Bob. Basically, Alice wants to say that I want to talk with Bob, and this is Bob's information. Then KDC generate a random symmetric key R1. KDC put first encrypt using Bob's secret key and encrypt with R1 and Alice information. Alice like a driver license number or some other unique ID information like a host name, IP address for Alice organization. Those information in the here encrypted using Bob's secret key, and then plus with R1, then encrypted again using Alice's secret key and sent to Alice. So this one can be decrypted by Alice, right? Because this is encryption by Alice key. So then Alice knows that R1 is a key that I should use to talk with Bob. So Alice will know R1 now. But this one, Alice cannot decrypt it. Alice basically forward this one to Bob. Bob can decrypt this one because this is encrypted by KB KDC. So Bob is able to decrypt it. And Bob knows that, well, Alice wants to talk with me. And R1 is an encryption key that is going to be used for this communication. So Bob knows that use R1 to communicate with Alice. Then Alice and Bob, they can communicate using this R1 for their communication. So in this way, this R1 is a shared secret key between Alice and Bob, and both Alice and Bob can get this R1 in a reliable way. Of course, this R1 is known by KDC, but it does not matter. KDC is trusted by everyone, right? So in this way, this R1 is called a session key, has been successfully disseminated between Alice and Bob under the help of the KDC center. So it's called session key because this key is only used for this communication session. Once A and B finished talk to each other, when they close the connection, next time when they want to talk to each other, they need to go through the same procedure. They will get another session key to be used for their communication. Okay, any question for this procedure here? So first, the KDC never share each user's secret key with each other. So each user's secret key is only a shared secret between KDC and that particular user. KDC never disclose this key to other users. So we should never use session key equal to one of the user's secret key. The KDC always generate a session key on the time when it is needed. And this encryption is required to make sure that Bob knows that Alice wants to talk with me, and this is R1 Alice wants to use. I should not receive them in plain text sent by Alice. Otherwise, other attacker knows this. And this encryption have to be done by the KDC. Otherwise, it cannot be decrypted by Bob. This has to be encrypted by KDC. Because when Bob can decrypt it, then Bob can trust this decrypted result, because this encryption can only be done by KDC. So if I can decrypt it, Now I know that this information is generated by KDC. KDC tell me that Alice want to talk with me, and this R1 is a session key that I need to use. So this is a KDC way. This is doable, but this architecture has one big requirement. It requires every user to register with the KDC, which is not feasible for the internet, because in internet, most users are normal user. You don't have the resource to register with a KDC, because register a secret key with KDC, you need to pay the annual fee to the KDC. A normal user don't do that. So in the internet, the real usage is this certification authority way used for public key dissemination. Basically, when Bob wants to disseminate his public key in a reliable way, Bob will physically go to this certificate authority. It's just like KDC in the previous scenario. Bob will physically go to the certificate authority, presented his public key. Then this key will be encrypted by the CA's private key. So each CA has its own private key. And this private key will encrypt this KB+. So this one is called digital certificate. So it's called certificate, digital certificate. So this encryption by CA's private key. Then, then when Alice wants to get Bob's public key, Alice can ask Bob to send this certificate. So this certificate was sent to Alice. Then Alice will use a corresponding CA's plus public key to decryption on this to recover KB+. If this certificate can be decrypted by using KCA+, then Alice can trust that whatever decrypted result is Bob's public key, because it is encrypted by the CA, so I can trust it. And you can see that this encryption is similar to digital signature. This CA is basically authorized this KB+. So this is actually used in the real world. Let's show the basic procedure. In the real world, only those servers have certificate for their public key, because only server need to disseminate their public key out to every users. So when a web server, suppose we use web server as example, the web server use a side channel to send his public key to the CA. Then CA generate this digital certificate and send it back to the server. Then when a web client connect to the web server using HTTPS connection, the HTTPS connection, after the three-way handshake, the client, basically the web browser, will send a certificate request to the web server. The web server will send this digital certificate back to the client. Then the client use the corresponding CA's public key to do the decryption to recover the KB+. So after this recovery, then client know that this KB+ is trustable, because this is a sign certified by that CA, so I can trust this KB+. Then the browser generate this symmetric session key and also a random number encrypted by this KB+, sent to the web server. This one can only be decrypted by the web server, because this one can only be decrypted by KB-. So then the web server will know this symmetric session key. Web server use a symmetric session key to encrypt this R. This R is called a nonce. Basically, it's just a random number, and generate this encrypted random number sent back to the browser client. So this random number is used as a challenge and response. If I tell you a random number, if you can tell me back what is random number, then I know that you have get this KAB successfully. So I know this is a live communication. This random number is trying to deal with this so-called replay attack, because attacker, when they eavesdrop some data, they sometimes they can eavesdrop that packet, then replay it like 1 hour or 2 hours later. And this challenge and response, this random number can deal with that replay attack. After client receive this, then following communication, they always use that symmetric session key for the encryption. So this will hold the data to be secret between A and B for all the communication following. So this is actual principle, the protocol for the HTTPS communication in the World Wide Web. And this is a foundation for e-commerce. Otherwise, the e-commerce, the banking, online banking, they will not be successful, because when you connect to Amazon.com or when you connect to your bank, you don't know whether you are connecting to the real bank server or you're connecting to a fake bank server. And this digital certificate can make sure that when you get this digital certificate, you can verify the web server you connected is really the Amazon or really the bank website. And this is used in the HTTPS connection. And basically, when you connect to any website, if this is HTTPS, it will show, the URL will show a lock. If you click the lock, it will show that the connection is secure because this is HTTPS connection and the browser has verified the server's public key. And you can see this public key. Well, this is the Google Bing. It doesn't have an easy way. Okay, maybe connect to learn more. No, this is not. Yeah, I'm not familiar with how to see the digital certificate in Bing. Let me use Safari. For example, if we connect to my UCF.edu, and this connection is HTTPS connection. It has a lock. If you click the lock, and it will say show certificate, then you can see the certificate is that this digital certificate is generated by this RSA server CA2. And so in internet, there are many certificate authority. It's not just one certificate authority, because one certificate authority will create a bottleneck. In internet, there are dozens or even hundreds of certificate authorities out there. So when you want your own web server to have a digital certificate of your public key, you can go to one of those certificate authority to pay the annual fee. Then that certificate authority will generate the digital certificate and send to you. So UCF, my UCF, the digital certificate is generated by this certificate authority. And details, well, this is too small. Let me use maybe Google Chrome is easier to see. So this one, when you click the link, you can see this connection is secure, and you can see this certification information. So this is a digital certificate for my UCF. It tells a lot of information about the digital certificate. This digital certificate is issued to UCF, issued to this common name is basically for this website. This is official domain name for this web server, and issued by. So this is a certificate authority who generates this digital certificate, and this digital certificate was generated 2024 and expired in 2025. So we need to pay annual fee to the certificate authority for every web server we generate digital certificate. And it showed this SHA-256. Remember, this is a hashing algorithm. SHA-256 means this hash value is as 256 bit. This is the hash value for this digital certificate. Because digital certificate, in my illustration, I say that this is, in my illustration, I say this is a digital certificate, but this is just a concept. Digital certificate is much more than that. It contains a lot of text information, like the web server's name, the organization, the expiration time of the digital certificate, the CA's name, a lot of information. So the digital certificate is actually all those information in plain text plus the digital signature for all those information. Remember, digital signature need to use a hashing algorithm. That's why here it showed what is the hashing algorithm used in that digital signature. And if you want to see the details, you can see that this is actual public key certified by the digital certificate. So this is actual public key for my UCF. In my slides, I say that the digital certificate is here. It only contains the public key, but actual digital signature contains not only the public key, but a lot of other text. The actual public key in this digital certificate is this subject public key is this one. You can see this public key is 4,000 bit, so it's a very large public key. And public key algorithm is RSA encryption, so it's still using RSA algorithm. So this is how you see a digital certificate. If you connecting to a website not using HTTPS but use HTTP, you can see that this URL, it will give you this warning, not secure, because you are using HTTP connection. There's no encryption here. There's no digital certificate verification. Of course, for this website, it supports both HTTP and HTTPS connection. When you use HTTPS connection, then this is secure. It uses that, it verifies the digital certificate. Okay, so this page, again, this is a very important page for you to remember, to understand. When you understand this page, then you will understand how the current e-commerce, how the current commercial web servers works. How do they ensure the security between the client and their web server? This is how a client can trust the web server they connect. They will not be vulnerable that they connect to attacker's fake website because of this digital certificate. And it also ensures the communication is fully encrypted using this symmetric key encryption. and compared to the KDC way, you can see the advantage for this CA's infrastructure is that the client does not need to register any key. So client does not need to pay any annual fee. Only the servers need to pay the annual fee to certificate authority to obtain this digital certificate. So if you don't want to pay the certificate fee, then your website may be vulnerable to fake attack. If you connect to a website using HTTPS connection, but fail the certificate verification by browser, if you have a failed connection, if you connect to a web server using HTTPS connection, but the web server does not purchase any digital certificate, then your browser will give you a warning saying that either your connection is not private or some other warning like SSL error. Basically tell you that the browser cannot verify the public key sent by the server. Then ask the user whether you want to continue the connection or not. So that's where you connect to some web server and your browser give you the warning. These all kinds of warning by the browser. So this is CA-based infrastructure. Its security is rely on three features, three assumptions. First, the browser have built-in CA's public key. Remember, when browser get the certificate, browser need to use the corresponding CA's public key to verify the digital certificate. So browser need to have this CA's public key beforehand. And because there are only limited number of CA, like there are only dozens of CA out there. So it's very easy for the browser to hard code all the CA's public key in the program itself. So as long as you are using a real browser code, then you don't need to worry about the first issue. So browser have built-in CA's public key. So that will solve the initial chicken egg problem. Secondly, CAs are trustable. If one CA has been compromised, then attacker can use that CA to generate a lot of certificates by themselves. Then the browser cannot verify that these are fake a web server anymore. Third is that web server have certificate. So web servers have purchased the certificate. If a web server does not purchase the certificate, does not pay the annual fee, then the browser cannot verify because the browser does not have a certificate signed by any CA. Browser can only send that certificate directly to the server have to send that certificate directly to the browser. So browser cannot verify it. So these are the three assumptions in order for this CA-based infrastructure work. This CA-based infrastructure is called a public key infrastructure. It's is called public key infrastructure. It's called public key infrastructure, PKI. Public key infrastructure just to refer to whatever I showed in that page of slides. Of course, Wikipedia explanation is much more detailed, but at the same time, much harder to understand. I believe this page will demonstrate the concept in a much easier way to understand. So an actual certificate, as I said, an actual certificate contains a lot of text. Then all this text will be generated by the CA as a digital signature. So you can see that this is a text. The text contains the public key, contains the server's information, contains the CA's information. All those information, then they go through this MD5 hash, then CA's private key will do the encryption. So this encryption you can see is the digital signature, right? So it's the CA generate the digital signature of all this text. Combined together is actual certificate. So the PKI, public key infrastructure for World Wide Web, is used only for server authentication, not client. This is only to verify the server is authenticated. The client does not matter. The client does not have any public key for this certificate verification. It's only for server authentication. If you connect to a server that does not have a public key, like SSH connect to SSH server, most SSH server is a Linux server. They don't purchase this digital certificate because certification require annual fee. So all those Linux server, SSH server, when a client connect to it, the first time connection, the SSH server basically send the public key directly to the client. Then the client will ask, do you trust this public key sent by the remote server? If you trust it, this key will be saved. Then later on, it will always use that key for the communication. It's just the first time communication, you have the risk that you are connecting to a fake SSH server, not to the real one. So initial setup, you have to trust the first time connection. Then after that, the client will save the server's public key, and from that time, you always use that public key. Okay, so all these communication, like this communication need a multiple round. What if we want to do just a one round communication? We don't want too many round trip back and forth. And then this showed how do we do this secure, reliable communication in one round. Suppose this is business to business. Both Alice and Bob, they have their public key certified by certified authority. Suppose these are two businesses, they communicate with each other. And public keys are pre-distributed securely already. So both A and B, they have their certificate. If Alice wants to send a confidential message to Bob, Alice generates a symmetric session key, then use Bob's public key to encrypt it. Alice uses symmetric session key to encrypt the message. Then these two concatenate together. This plus just means concatenation, just to put them together, then send it through internet to Bob. So this KS is a symmetric session key generated by Alice. Then when Bob receives it, Bob will first use his private key to recover the symmetric session key. Once he recovers symmetric session key, he uses the symmetric session key to decrypt the encrypted message to recover the original message. So this will ensure the confidentiality. And remember here, there's no back and forth. It's just a one-way delivery. It's just like a mail delivery. It's just a one round. And what if Alice just want the message authentication and integrity of the message? She doesn't worry about the message being exposed to the public. So she will just using her private key and this hash algorithm like MD5 to generate the digital signature. Then combine the digital signature together with the message M and deliver to the Bob. When Bob receives it, Bob will compute the hash function, hash value, recover from the digital signature by using sender's public key and compare the hash value. If they match, then Bob knows that the message is really generated by Alice and has not been modified by anyone. So this is, but here there is no confidentiality. It's just ensure of the message integrity and message authentication. If you want to combine both the secrecy and the sender authentication together, you can combine the two operations together. Like first, Alice generate a digital signature combined with the message to guarantee the authentication and integrity, because this is a digital signature. Then Alice generate a symmetric session key to encrypt everything, to make it confidential. Then Alice use a receiver's public key. Remember, this is Bob's public key. It's not sender's public key. Receiver's public key to encrypt this symmetric session key. This is for key dissemination. Then put together, send to Bob. So in this procedure, there are three keys used. Alice, the sender's private key for message authentication and the signature. Bob's newly created symmetric session key for actual data encryption. Then receiver's public key for key dissemination. I want to disseminate my secret encryption key to the receiver. So I need to use the receiver's public key for that key dissemination. So there are three keys used. In the receiver and in Bob, you just do the same procedure in the reverse order. And you can decrypt the message. You can also verify the digital signature for the message, which is the hash function and message authentication code. Hash function we introduced the last time. It's about cryptography hash, which is used widely in digital signature, where it used to calculate the message digest, or we can say message fingerprint for any arbitrary size of message. Then, so that is a cryptography hash. One requirement for cryptography hash is that given a hash value, you don't have an easy way to find a message that can generate that hash value. So basically, it just means the one direction is very easy. From the message, you generate a hash is very easy and very fast. On the other hand, giving a hash value, want you to generate any message that will map with that hash value, which is almost impossible. It's a computational impossible. So that's a cryptography hash requirement. And cryptography hash, actually, the design is very similar to DES, to the block symmetric encryption. The widely used cryptography hash that widely used is first is by this Rivest, one of the researchers in the RSA algorithm. So he is a mathematician, and I don't know whether he died or not, but 20 years ago, he was a professor in MIT. MD5 is a version 5 of this so-called message digest algorithm. Previous version, they have this or that problem. So MD version 5 is very mature and has been widely used for a long, long time. It's just in 2000, I don't know which year, there's a publication showed a vulnerability in the MD5, which can make this guessing of the message easier than before. Originally, you have to do exhaust all possible design. Basically, there's no clue for you to generate a message that can have a given hash value. That research shows that given a hash value, you can shrink down this guessing space where you can generate the message that have that hash value. So after that, the government began to use SHA-1 for the hash as a second generation. So MD5 will generate a hash value basically is 16 bytes. So it's very small. It's 16 bytes. No matter how big the message is. However, this hash value is actually has a very large space because this hash value is 128-bit. So that's, you can see how many possible hash value. It's a 2 to power 128. So that's a very, very large hash space. So even though there is a possible collision, because the hash value only 16 bytes, it has limited number of possible value, but for the message, it's unlimited. The hash value is a mapping between this unlimited size of space to this 2 to power 168 space. So it's a very infinite space to a limited space mapping. So hash value, hash function, inherently, it will have collision. Basically, it's possible that you can find two messages that generate the same hash value. It's just that this design makes it reverse is impossible. It's just like in the current world, it's possible that two persons will have the same exact fingerprint. However, given you a fingerprint, you don't have a good way to find a person that have that fingerprint. So basically, that is a similar reason. So this is a standard. It has been used for a long time. The MD5, this is description, how it operates. The word description is hard to understand, so we will use this graph description. This is a graph, I believe I copied from the Wikipedia. So basically, the message will first add some padding. So this is arbitrary size of message. Because it's using the same way as a block cipher to do this calculation. So you need to make sure the message is basically after padding, it's n times, it's L times of 512 bits. Because every time it deals with 512 bits as a block to do this operation. So it needs to be this size. So if the message is not that size, you need to do some padding. The padding basically, at the last part, it will have the message length, basically k modular 2 to power 64. So that's that basically denote to tell the receiver how big the message is, and the remaining padding is just to make sure that everything entirely is L times of 512 bits. So that's a padding part. After you have padded the message, you break this message into 512 bits block. So there are many block from 0 to L-1 block. Then for every block, you feed it to this MD5 algorithm. And the algorithm will have two input. One is a message, another is another input. For the first block, the first initial value is this input 128-bit is called initial vector, initialization vector. So it's a predefined fixed value. Remember, this is not encryption. For encryption, this input should be your encryption key. But for this MD5, there is no encryption key, so everyone should use it in the same way. So initial value is the fixed predefined value. Then feed in. So this MD5 is very similar to DES encryption, symmetric key encryption. Basically, one input is encryption key, another input is a block plain text. Then the output is 128-bit. The output will feed into the second block processing. Another input is the second block. So you just do this repeatedly until you finish the last block of the message. The output will be the message digest. So you can see that no matter how large the message is, you just repeatedly use MD5 block algorithm, do it repeatedly until you finish all the blocks. So its computation time is a linear increase as the message become larger. Its computation time will be linear increase. The MD5, this operation block, is actually very similar to DES encryption. This is a CV vector, basically this 128-bit input. Another input is data. Another input is this data part. Then it will be inside MD5. It will break into four steps. In each steps, there are 16 steps in internal operation. So this 16 step is very similar to the DES encryption, that 16 steps. And so A, B, C, D, each one is 32-bit. Then this one will split into 4 sections feeding into them. And after that, this is XOR. So XOR with this initial CV vector, and output will be this next CV value. This is not XOR. This is addition. This is adding operation where you just I think it's not ignore the carry on bit. Carry on bit will be add back to the beginning to add again. So that's the addition. So let's come back to the word explanation. The pad message will always be 1000 something. This pad message is try to make sure that it is become a full block. And the last part, 64-bit, is the message length. So it's just like in TCP packet header, you have a packet length. IP packet header, you also have a packet length, that kind of field. So processing message in 16-word blocks, and so that's output. So this is MD5, and when MD5 become not secure, oh sorry. It was replaced by SHA algorithm, SHA algorithm. This algorithm, you can see this processing is almost identical to MD5. You can see the operation of the SHA1 looks exactly the same as MD5. Because MD5 is like DES, all the encryption, all the processing is very mature. When MD5 finds the vulnerability, people try to modify the MD5 such that that vulnerability will be resolved. So this SHA algorithm is basically try to resolve that discovered vulnerability in this MD5. But the basic overall architecture is still the same. It's just in each part, this substitution box will be changed. Just like DES, you have substitution box. This one also have substitution box. So that has been changed. And this SHA-1 will generate 160 bits of the hash value. 128 bit is big enough, but since the computer will become more and more powerful, when we revise it, why not we increase this hash value size? Instead of 16 bytes, right now it's 20 bytes. Still, it's still a very small amount of data. So the hash value is 20 bytes. And there are some variation of the SHA algorithm. This variation basically means that you can generate a hash value with a different size, 256 bit or 512 bits. So if you generate a bigger size of hash value, you will reduce the possibility of collision. Remember, they are still possible of collision. So if you increase this hash value space, the collision possibility will be correspondingly reduced. Then you don't need to worry about collision anymore. Because collision basically means that two messages, they generate exactly the same hash value, which will make this digital signature or message digest all have some problem. But of course, when you increase the hash value size, the computation will correspondingly increase. So you should use one that is suitable for your system. Compatibility with increased security provided by AES, and the structure similar detail is similar to the SHA-1. Just like last time when I showed the digital certificate, like if I want to see Bank of America, like if I want to see Bank of America digital certificate, like you click this lock. This is a Safari browser. Safari browser showed you can show certificate, and this is the certificate information. Well, it's a little bit small, but if you click this detail, you can see this certificate. This certificate is issued by this Antitrust Cooperation Authority, so L1M. So that is a certificate authority who provide the digital certificate to Bank of America website. And this certificate detail, it will show the serial number. You can see this. This is a hash algorithm used, signature algorithm. Remember last time I mentioned that the digital certificate, it actually has a lot of things. Let me see. Digital certificate, the actual digital certificate is basically a lot of plain text. The CA's information, this web server's information, the web server's public key, all the information in plain text. Then it has a digital signature generated by the CA. So in this digital signature is basically the CA's private key encryption of the hash value of all this plain text data. So here in the digital certificate, this hash function is also used. So there is a hash function used. That's why here you can see this hash function used in the signature algorithm is SHA-256. This public key encryption is using RSA algorithm. So public key encryption, there are many other algorithms. RSA is one very popular one, but there are several other public key algorithms out there. So it showed this This is the public key algorithm is RSA. And this public key is 256 bytes. This is the size of the public key. If you want to see more, you can click and you can see this is the entire public key. So that's why I said that in digital certificate, everything here is public. This including this server public key, server's information, CA's information, everything is all in plain text. It's just the certificate authority will generate the digital signature of the entire plain text. So no one can modify this plain text part. But in our notation, we say that this is a digital certificate. The notation, to better explain the concept, we say that this is a digital certificate. Basically, the CA's private key encryption of this server's public key. Okay. So that is this digital certificate information, and you can see more about this. It has much more information than we can understand. Okay, I think here is a fingerprint. Fingerprint, it actually generated two fingerprints, SHA-256 and SHA-1. It's just for any client, whichever hash function you can use one of them. So this is a fingerprint. So instead of one digital signature, this certificate actually has two digital signature. One is based on SHA-1 hash function, another is based on SHA-256 hash function. Okay, so that is cryptography hash. Basically, two are mainly used, MD5 and this SHA algorithm. Message authentication code it's usually acronym is called MAC, but don't confuse this MAC with the MAC address of your computer. MAC address of your computer is your network interface card. It has a data link layer address, so that is called a MAC address. Data link layer address is 6 bytes. So instead of IP address 4 bytes, data link layer, this MAC address is 6 bytes. Don't confuse this MAC with that MAC, even though they have the same acronym. This MAC, message authentication code, you can see the name is authentication of the message. To make sure that when receiver receive it, it can verify the message has not been modified by anyone else. It is generated by the true sender. The assumption is that the sender receiver has a pre-shared secret key. So this is one big assumption for this message authentication code to work. The sender and receiver has a pre-shared secret key, like a symmetric secret key. You can think that this is a digital signature only using symmetric key, not public key cryptography. In digital signature, we introduced before, it is based on public key cryptography. Message authentication code try to achieve the same purpose, but it doesn't use public cryptography. It uses symmetric key cryptography. The message authentication code will be appended to a message as a signature. You can treat the message authentication code as equivalent as a digital signature. It's just doesn't use public key cryptography. Okay, so message authentication code is basically the message, you first go through an encryption. You go through a hash function, then an encryption. This K is this secret encryption key. This message authentication code is basically this secret key plus the message. You calculate the hash value. So the hash value will be appended to the original message. So this is a message authentication code. This is original use. You have the secret key. You don't do any encryption. You just concatenate this secret key with a message. Then you calculate the hash value. So the result here is a hash value. So if an attacker get this message, attacker cannot recover this secret key K, because what saved here is just the hash value. So attacker does not know the K. But for the receiver, the true receiver, because he has this key K, he can do the same operation, then compare with this hash function, hash value. If they match, then the receiver know that the message is generated by the true sender who shared this pre-shared secret key with me. So this is very similar to digital signature. It's just, remember, it's equivalent to digital signature. It just doesn't use public-private key encryption. So this is a concept. You simply don't need to do any encryption. You just concatenate, then calculate the hash. So this computation is very quick. There's no encryption. You just calculate hash. Hash computation is very efficient for the current computer architecture. Remember, here is to authenticate the message. It doesn't try to keep the message secret. So it doesn't provide confidentiality. It provides integrity of the message. So the message is still in plain text format. So message authentication code is mainly used for archive reason. If you want to save something in a public database, you don't worry about anyone read this data, but you want to make sure the data integrity has been protected. Of course, you can use encryption for secrecy, but message authentication code just use hash function, so it's more computational efficient than using encryption. Sometimes only authentication is needed. If you need to keep the message secret, you can use encryption to encrypt the entire message. So that will be slower than this message authentication code. So message is not a digital signature. Digital signature is referring to that public key cryptography way. It will require both sender and receiver use a pre-shared secret key. So it's based on a pre-shared secret key and hash function. So because hash functions are generally faster than encryption, and that's why this MAC can be used in many cases. The original proposal for this MAC is that you simply concatenate the secret key with the message. This just means concatenate these two texts together. You calculate the hash. However, this way to calculate the hash, it has a vulnerability because this key is very small. The message could be very long. You concatenate this very small secret key at the beginning, keep the big 99% of the portion to be intact. Then this hash value computation is, people have discovered that this way to compute hash, it has some weakness. So we should not do this in this straightforward way because this has some weakness. And eventually people developed this HMAC, hash-based message authentication code. This algorithm proved to be much more secure than this basic content concatenation way for the MAC computation. So we will introduce what's the HMAC. HMAC, the math operation is represented by this, which is a little bit difficult to understand, but there are some graphic representation of the operation of the HMAC. Basically, this is a message. Instead of concatenate the key directly with the message, the key will be XORed with so-called iPad. So this iPad is predefined. So remember, here is not encryption. It's just a hash computation. So iPad and OPAD, they are predefined 64 bytes value. They are predefined 64-byte value. The key first XOR with the iPad on this first 32 byte. So the key need to be 32 byte. Then this value will be concatenated here. And then you calculate a hash value for this. So this is hash value. Then the hash value will concatenate with this O keypad. The O keypad is calculated in the same way. Key XOR with this OPAD. So that is O keypad. And then you calculate the hash function again. So in this operation, the hash function will use twice. Instead of one time, it used twice. And then it will calculate the final message. But the second time when you run the hash function, it's very quick because the message could be very long. The message could be megabytes, gigabyte. But the second time when you run the hash function, this is just 64 bytes plus for SHA-1 is 20 bytes. So it's only 84 bytes. So second run of the hash function is very quick. You can think that computation time is ignorable. So it will still keep this running speed feature of the MAC code. But through this operation, we can remove that weakness when you directly concatenate the key with the message. So this is HMAC, how it operates in the real world. Okay, so you just need to, for here, I don't need you to memorize everything here because it's a little bit complicated. You just need to know this HMAC. It uses a special operation on this key and message. And just need to remember the idea of this MAC code, why it is used MAC code instead of full encryption. Because it's efficient, it's equivalent to digital signature, so it can still maintain this message integrity, but it's more efficient than encryption of the entire message. It's also more efficient than using digital signature. Remember, digital signature need to use public key cryptography. Public key cryptography, generally speaking, is much slower than symmetric key cryptography. Okay, so that's all for this